Okay, so I think the recording started, so we can go ahead with the tutorial on the QIBO implementations.
Do you see my screen?
Yep, we see a notebook on the localhost on DBF.
Yes. We decided to go on with a notebook form of the tutorial because maybe it's more suitable or easy to follow. And yeah, so I will speak for also Eduardo and Andrea. And if you want to interrupt me, correct me, whatever, please go ahead and do that. And okay, so basically we are going to perform a diagonalization in a notebook form. And what we do is try to, this is not a tutorial only for us, probably. It's just, we were thinking about something more in general. So probably we cannot spend a lot of time on the details that you already explained us. But okay, in principle, what we have here is, okay, we start by importing something quite useful for the tutorial. These packages here are just Python packages that can be useful for data visualization and linear algebra. Then we import hyperopt. Hyperopt is an hyperoptimizer. It's a package that we are now using in order to perform what you already did in terms of hyperoptimization of the step. And as you can see, we are importing the TPE. That's the tree-parsen estimator. That's not a grid search, but is a Bayesian technique to extract the step. But it's nothing more than, as far for the purpose of the tutorial, is nothing different from a grid search or whatever. And then we import from QIBO what we need. So in this case, we are going to use the Hamiltonians because we use the QIBO Hamiltonians objects. And then the set backend is just a way to define the backend because, as already Andrea explained the last time, QIBO has a modular form, and we can decide to execute the state vector simulation on different kind of engines, we can say, like TensorFlow, NumPy with accelerators, and so on. And then we import what we are interested in. So from the models double bracket file, we import the flow generator type and the double bracket flow objects. Yes. So now I will explain you a bit more about these two objects. Here just we have some plotting function that can be useful during the tutorial. And stop me anytime you have any question. So, okay, in order to do something more physical, we decided to take into account a transfer field Ising model to be diagonalized. In particular, we have this Hamiltonian here, with n set to be 6 and h set to be 3 in this case. And okay, let me compile before I execute, before I forget. Okay, so now we are importing the plotting function. And now what we do is to set the backend. In this case, we are going to use QIBO. It's not necessary in the sense that we are using a few number of qubits, but still the performance of QIBO, as Andrea showed you the last time, are very similar to NumPy. So the default one is QIBO, so we go on with QIBO. We define the Hamiltonian. Oh, here is 5, but you see.
Yeah.
6.
Also, Matteo, you may want to change the second QIBO to number.
Ah, yes.
Yeah, maybe it was a typo from my side. Sorry.
No problem, no problem. And then, okay, we can use one of the plotting functions to visualize the Hamiltonian. Okay, so this is what we have now, the beginning. And yeah, nothing more. So typically with an Hamiltonian in QIBO, you can call the matrix form by typing Hamiltonian.matrix, and you have the complex matrix that represent the Hamiltonian. And we are exploiting these for the plotting functions, but yes, nothing incredible. Here we just summarize a bit the options provided by the reference, that's the double bracket flow paper, in which basically we just introduce the concept of the generator of the flow, and then introduce the 3 ways we implemented the generator. So what we call canonical generator, in which we exploit the diagonal form, the diagonal form of the Hamiltonian, and then using the single and the group commutator. I think probably this step of the tutorial will be one of the most important to be reviewed by you, Marek, in the sense that maybe we are okay, maybe
Yeah. So I'm
you know.
finishing this resubmission, and now, for example, I'm talking more about iterations, because iterations can approximate the continuous equation that you wrote. So this H sub L, but when you write HK, we just are dealing with a recursion, and then we just iterate. So that's only one thing that will change. So so for example, the curly notation can signify the continuous flow, which can be eventually approximated by the iterations that we will study, I think, next. But it's extremely costly. It's very unstable to approximate it, and we don't need it, because that's so we go more variational next. Yeah, I think this is. Can you just tell me, if you will be running the single commutator, then the input will be some matrix, and that matrix will be used as decay. Yeah, so that will be some input there.
Yes.
While, for example, for the canonical in your implementation, there's essentially no input, because you just take the Hamiltonian that you have and you dephase, no?
Yeah. We are going to show also this, I think, now.
Yeah. And do you also split between preparing what the generator will be and then just taking the exponential with some parameter s, or do you do it in one go? I guess you will be showing that, no?
Yeah, I think we are not going to open the double bracket code, but if you want, we can. But
No. Okay, yeah. So just to sometimes know, like what will be the inputs, and the commutator should be clear. So yeah, okay, yeah, just thinking out loud. Okay, I think so far we understand everything. So thank you.
Okay, fine. Okay, so jumping here to the code, as I was saying, we have two classes basically that interacts between them. One is the flow generator type class that contains basically all the generator. And if we compile this class, for example, for looping on the flow generator types, we have all the available generator that are the canonical, as I said, single group and single commutator and group commutator. And then, as we were discussing, we should select one of them. I mean, we can select one of them in order to initialize the double bracket flow. But still, the double bracket flow then is dynamical in the sense that you can decide to perform one iteration with whatever generator you want to use. So in this case, I'm setting flow type equal to the canonical one. And then once this is done, what we need to do is to define the double bracket flow. And for doing this, we have, as I say, the QIBO models double bracket flow class that can be initialized like this. So in this case, I'm using a deep copy here because I want to be sure that we are not overwriting stuff in the notebook, but in principle, in the code is everything is fine. So, okay, the DBF is the double bracket flow in which we pass two arguments, the Hamiltonian and the flow type. If the flow type is not passed, by default, we set the canonical one. This is how it works. Then this is just a list of the features we implemented in the double bracket flow class. You can call directly from the double bracket flow the backend, just to be sure what you are doing. We can print, we have access to the initial form of the Hamiltonian that's saved and casted like dbf.h0. And this h0 will remain the same forever. because it's important, we guess, to keep track of what we are doing. And so, yes, we can have access to the matrix form of the H0, or like we already saw before in a more graphical representation.
So can you comment which part is general and which part? So is this tightly linked to QIBO? So for example, the formats would be, if I would use, for example, some other model like adiabatic and so on, would some of the structures here would be similar?
Okay,
or?
for now, I think the answer to your question is that for now, what is general is the Hamiltonian definition and the double bracket flow usage. What is customized in this tutorial is just the plotting function. Whatever else can be used.
Okay. Well,
Because as we
that's also
already
a good
discussed.
answer because this stuff is not too complicated in the end. Also. Yeah.
Yeah, no, the idea was to do something very, very easy to keep familiar. I mean,
Yeah. Okay, thank
take
you.
familiarity with the code. And okay, then we just wrote this visualize drift function. That's not super important, but just to see what happens if we benchmark the two metrics, the H0 and the H matrix, in order to see what happens during the evolution. So for now, we have basically the same metrics. And just to, I mean, it's a tutorial, so we just wanted to show something more explicit. And okay, so what you can do more is to, okay, you can also visualize the diagonal part of the target Hamiltonian at any step of the flow. That now is quite weak, but we know it. And then you can compute directly from the, okay, here you just call DBF diagonal H matrix. In this case, is already in the shape of a matrix. Maybe we should consider to define it like an Hamiltonian, but okay, this is just discussion. And then we can have access directly to the off-diagonal norm that is useful in order to perform the optimization. And this can be accessed. This is linked directly to the H or HL. So yeah, the evolved one, if we already made it. So this is what is basically the skeleton of the double bracket flow class. But then the most important point is to use it. And we decided to go on with the fact that if you call directly the double bracket flow, so you execute the call function, you execute one double bracket iteration. So by default, again, if you pass to the double bracket flow call a generator, you perform the double bracket iteration with that generator. If not, the default one is called. And the default is the canonical if it's not set at the beginning. But one can decide to initialize the double bracket flow with the group commutator, and then in any moment decide to perform any kind of step iteration with another generator.
So there's the less supervised way with the dephasing. So instead of taking some arbitrary D, you take a diagonal D. Can you tell me if I would be using the group commutator, do I always need to give the D? Or if I don't give a D, but I'm using the group commutator, it will take the dephasing? Just to know how
we can try directly. In this case,
yeah.
in this case, the canonical one is, we can say what happens, but yeah, in this case, the canonical one is called by default. And so what we have is, the off-diagonal norm at the beginning is the same as before. Then we perform one step by calling the DBF with this step and the flow type, that's the canonical. And okay, we have the new diagonal norm. Or we can try to set another kind of generator. So for example, flow generator type.
For this, let me comment that for the other two types, which are like the single commutator and the group commutator, currently you always need to provide the matrix D.
Yeah, my idea was to make it crash, indeed.
Yeah.
And it
But
crashed.
eventually, if you think that it's useful, we can, by default, if the user doesn't pass anything, we can use the dephasing, as you were saying. Like this is
Yeah.
easy to
Though
implement.
I don't know if I would say that because this dephasing would be costly to implement. No, so
Mhm.
I think in practice, if we will be talking about actually running this on something, we would be heavily optimizing to find good operators D and supervise the progression. So Matteo, can you show us like some I don't know, NPI, what would be the notation? So if you use the group commutator, like if you would keep it still, sorry. And then what yeah, group commutator. That's good. That's helpful. And D will be the operator, yeah? Okay.
Yes, in this case, I think it's a generic matrix of the same size as the Hamiltonian matrix.
Yeah. So I could write D equals NPI on the correct size, and then I will not get any
Yes.
flow because it will commute, so it will be trivial. Yeah. So that
Yes,
will be
yes.
the
Or
notation there.
yeah, or eventually you can just pass the diagonal Hamiltonian as Matteo was showing by doing like dbf dot diagonal H matrix. It's a shortcut if you want.
Yes, we can do that in the end, indeed.
Yeah,
Okay.
and then the group commutator will
Let's
have
try
a
this.
little bit lowered action because it's only approximating the bracket. Okay, dbf diagonal.
This is just an example as we
Okay, so
were
this
saying.
will mimic the dephasing operation, yeah?
Yes.
Yeah. Okay.
Yeah.
And then I could also use the QIBO TFIM model and put H to 0, and that will give me the ZZ Hamiltonian, no? That could be also a quick example that I could try, or?
Yes, yes.
I think yes, absolutely yes. Yes, yes.
Yeah, Hamiltonian stop this. Okay, okay, thank you.
Yeah, but in QIBO, you can also build any kind of symbolic Hamiltonian mixing, whatever you want, because we use the symbolical pi, SignPy package, and yes, you can basically do whatever you want, either in the Hamiltonian way or using directly the matrices if you want to use NumPy or any.
Okay, so far everything clear. Thanks, Matteo. We are 20 minutes into the tutorial. Just
Okay.
but
And
this
okay,
is the
now
page that we need.
Yeah, just visualizing the drift to see if something is happening in the sense, yes, we are moving the Hamiltonian. And the final feature we wanted to show here was to hyper-optimize the step. So since we use hyperopt, what once is supposed to do is to call basically the double bracket flow as this function here, hyperopt step. That now is not in the official form because it's under review still, but it's quite close to the final form, I think. And yeah, basically you call the double bracket flow hyperopt step. You provide a range like here, in which you think the step should be. You provide a space from which sampling the new guests for the step, because this is the mechanism required by hyperopt. And then you provide the algorithm, in this case, the 3 Parzenov estimators. Maximum number of evaluations, and the verbosity if you want to see a loading bar, progress bar, but yeah, we should still think about this. The default mode is false. And what you see is, okay, now the matrix is quite, yes, it's 6 qubits, so it's taking some time.
Yeah.
Maybe we can.
And this kind of brute force search, even though we are doing few qubits, this is actually, it's not that easy. But I see that this hyperopt is actually going towards 1000 steps, yeah? So
yes, you can.
yeah.
See, basically what is doing here is to performing 1000 times the double bracket iteration at least. So,
exactly. Yeah.
I mean,
So
one can reduce a lot also because we saw that basically this jump of the loss function was reached at the very beginning of the optimization. So I think with just 100 step.
It was 1.9 or something. Okay.
Yes.
Yeah.
So the matrix is changing like this now.
Oh.
Okay. And if we want to visualize the drift, now we are in a more superposed. I mean, we are moving far from the H0. And okay, the last thing we wanted to show is how to perform a sequence of steps, quindi the algorithm, starting from the iteration. And yeah, just to show that in this tutorial, the method one is to keep the step fixed and just to perform the optimization. So here what happens is that we are initializing a double bracket flow with the deep copy, I mean a copy of the H Hamiltonian of the beginning with flow type, so canonical still. And we are just collecting here the off-diagonal norm history just to show it. And this is what we wanted to say the last time when we prefer just to do this outside from the class because it's quite easy to do. And okay, in this case, just 20 steps and we step 005. And just we call the double bracket flow with the defined step all these times and append the off-diagonal norm to the list. Okay, it's finished. And then we can plot what we get here. And the second method instead is how to maybe to use the hyperoptimizer. In this case, we are not super expert, so we define this strategy here, but indeed, we are working on the optimization side, so maybe this part will be renewed. But okay, this is a second double bracket flow. Again, we want to save the off-diagonal norm history, but at this time we perform an initial hyperoptimization to find a step. And then since maybe the first step is not the best one during the evolution, we then ask at each step a small optimization to be performed. And of course it's, okay, this is the big optimization, the initial big optimization. As you can see, much slower than the initial one. And then we optimize the steps every time. This is finding the best step for each evolutionary step. I tried this with 4 qubits, so now is a bit slower, but I think it's going to finish.
So you see it just before it jumped, and sometimes that happens if it builds up some iterations, and at some point it can lift some degeneracy, and then a lot happens, so the step can be longer.
Yeah. And now we can plot the histories again. So what happens is that we have a faster convergence. So basically, I guess in 2 steps, we reach already a good configuration. In 3 steps, we are very close to the minimum reachable. And then we can visualize the final matrices that are closer to be diagonal.
Yep. And then
So
it
this
does
is
this plateau just because the delta comma sigma becomes very tiny. So it just stops there. Maybe later, if we have time, we could add some diagonal operator, any Ising model, and then maybe we can see that we can kick it down to start going with a single commutator. But okay, I think you have a few more cells that you want to show because I see the slider is almost at the end.
No, the only thing we can show maybe is how to review. And
Okay.
I mean to show you where this kind of stuff are in QIBO.
Maybe one,
And
can I make one
yeah, sure.
small comment? Yeah, I mean, now we're also able to evaluate the energy and the energy fluctuation at each step. And so then we can plot and compare the results.
You're right, sorry, Edo.
Sorry?
No, sorry, I think we were working on this before merging the pull request of the energy. I'm sorry.
Yeah. No, it's fine.
But then we could have a look in QIBO, and that will also show a little bit like how you guys code and how to find it in QIBO. So
yeah. Okay. So what is happening in QIBO now is that we have a main, if you want, main pull request. That's the, wait, where is it? The double bracket flow one.
Yes.
and
That
what's
is
this
the
acronym WIP? Because
work in progress.
Work in
a
progress.
work in
work in
progress.
progress.
Yes.
Okay, yeah. And then within that work in progress issue, you have the smaller ones, no? Because I see also above in the second line is DBF step
Yeah.
optimization.
We
And
have then the specific pull request in which we work to fix things or to implement new features. And then once we all agree about them, we merge them into the work in progress until we are ready with all the features we wanted before merging into the main of QIBO.
so if we would like to check, for example, quickly what Eduardo said with the energies, we would just click on Eduardo and see what he was pushing, or
in this case, it's already merged here, so we just can go to the, maybe let me go directly to the code. We can go in the DBF branch of QIBO, in which already we have the double bracket flow model. So you go to models, and double bracket.
Okay.
And here you have the code. That's basically all the code.
Yeah.
And so this is the shape of the flow generator type. And okay, let's see what was saying Eduardo. The energy fluctuations are here, for example.
And okay, and this will work similarly to those histories that you were showing, or how to understand this?
Yeah, I mean, the energy fluctuations, maybe Edo, you want to comment it, but
I mean,
think
given a
using just...
state that is a list, I mean, you evaluate the energy expectation value. And then, I mean, like, then you make the expectation value of the square of the Hamiltonian and subtract the two terms and make the square root.
Yeah. And now if we would be doing this in the tutorial, because like it's not pulled, but we were looking at those of diagonal norms and so on, I would schedule it in, if I would make a sequence of steps.
Yeah, you can evaluate at each steps, collect in a list, and then plot the results.
Okay. Cool.
Yes. Okay. I mean, because we can evaluate the, I mean, Matteo, can you show the code?
Yeah, sure.
Yeah.
I was going to evaluate
I mean,
with the
okay, because we don't need a special method to evaluate the energy, because we already have in QIBO, as you can see in line 108. So with this one, we can evaluate the energy, and then we can evaluate the errors or the fluctuation, and then plot with the error parcels.
Yeah, I understand. Good. Then and Hamiltonian would be, for example, a class within QIBO, right? Provided or
yes, it's a QIBO model.
So it's just linked within QIBO, and that makes it shorter, and it's I'm wondering, so in QIBO you guys have some tests. I'm wondering if we should make some DBF tests or something like this to have some standardized examples.
There are already some standard tests that we implemented for those for that part of the code that we added. Okay.
Yes, if we go to the tests, now we have test model DBF somewhere here.
Yeah.
Typically we don't merge anything if we don't test it. So yes, everything is tested already here.
Because this can be like also nice as a tutorial just to see what kind of things you guys are testing, and that show the class a bit.
Yeah. So
But
here
typically,
as
the test.
yes,
Sorry.
Matteo, please continue.
No. Go on.
Okay, no, here I just wanted to show that this test is quite a very naive test. We are just creating an Hamiltonian with a random emission. Then we perform the evolution and we check that the off-diagonal norm is actually lower compared to the one at the beginning. So this is an example of a test that you can write in QIBO to make sure that the model is working.
Yeah. So I don't know of any analytical solution to those double bracket flows because it's like very non-commuting and it's kind of hard to cook it up. But we could try at some point. There's a different kind of double bracket which would have a different flow generator type, but it can interpolate between steps of the QR decomposition. So we could try to implement against something standardized, more standardized, which would be a QR decomposition step or something like this. So just to have like some comparison against something that we know from something else that it should work some way. But yeah, it's just thinking out loud. I think we saw many nice things. Maybe we could finish the tutorial with some open section and just try to see how you would pick up the diagonalization at the end stage of the plateau. So you showed us the optimization. That was one of the last plots. And then both are reaching some plateau, and that's not because of the scheduling, the timings, but it's because the generator type is kind of getting stuck. So for example, if I would like to if I would like to pick up at this stage, let's say, I mean, in practice, I would pick up somewhere here and consider some other diagonal operator. So I'm wondering, for example, if we would take some diagonal operator D equals Hamiltonian or something dot Ising model with 0 magnetic field. So we would have, like, maybe you could show us how to do Zi plus 1.
Are you watching? Can you see the screen?
Yeah, so it's Hamiltonian's Ising model, and I think next you need 6, H equals 0. Yeah. And okay, then you visualize. Okay, that's how it goes. So that's the D matrix. It might be too similar to what we already have, but I'm wondering if I could use this D to make one more step and see that, for example, the norm dropped a little bit. And then I think like that,
okay.
that will show how to troubleshoot.
Yeah, because we already started from the transverse field Ising model, so maybe. But yeah.
Yeah, but at this stage it could be different still, because it depends what's the diagonal of the steady state already. So if you scroll down, I think you're showing the diagonal matrix or not? Because sometimes the scale of the plot is not showing the matrix elements and.
Sorry, I don't understand what you want to see.
Okay, so this might not lower the norm, but we saw the plateau. So I'm wondering if we can add by hand one more cell where we pick up after step, I don't know, 20, the last step that you had, and just do a single commutator type of the generator and put this D matrix as the D matrix.
Sure.
Yes.
Okay, so
it should be doable.
we can go here. Like, for example, if S is equal to, okay, we were 10, I say, 12, we can go like 14. 14. So just let me copy here the D matrix. Okay.
And just experiment whether that will kick it further, and let's see.
Let me just recompile this cell in order not to have too many. stuff in the lists. Okay, and so if the step is this step, we just say dbf. Okay, yes, dbf2 in this case. We say, wait, yes, step equal to step, mode equal to flow generator type single commutator, and d equal to d.
That's how you would do it.
But
Yeah.
should be a d dot matrix, I think.
Yes, I think so.
Matrix. Okay.
And then we say else, right?
Yeah, and then maybe you switch back to the.
This one should be here. Okay. And yeah. Okay. So only if the step is this step, we perform a single commutator step.
DBF of no arguments is the other option. Okay. And can you tell me maybe we should put this back because in like we do either this step or that step, but we still store it or
You're right. This one should be like here, like this.
Yeah, maybe. Yeah.
Yeah.
That was
You're
my
right. You're right. Yeah.
Okay. Yeah.
So let's try. Maybe I will run a smaller optimization.
So now it's repeating what we had before, and this is also answering my question before because I could open a new cell and write dbf to step with this. I could write this after, and that would add one more step afterwards. No, it's just I would need to change the code a bit.
Yes.
Yeah. So it's kind of step by step iterative. That's the code.
Seems it quite similar to before.
Yeah. So I think we wanted something to happen around here, but not much happened. So yeah.
Yeah, here.
Okay. Though maybe you could still point me because I think we can finish the tutorial here. But let's say if I would like to do some ansatz for optimizing this, I would consider diagonal operators of the form GIJZIZJ. So let's say I'm writing it like in LaTeX, and you said that QIBO can use this SymPy stuff to create the Hamiltonians.
Yeah.
Maybe you can point us somewhere like how you would create the Hamiltonian. It might take too much time to try out. So we tried something where this was more or less unity and it was a very homogeneous model. It didn't kick it anywhere. So if we would be trying something else, we could try something else.
Yes, I want to show you directly the documentation that maybe is the best way to do this. Symbolic Hamiltonian. Someone should be. Yes. Somewhere here.
So QIBO.science and then symbolic Hamiltonian. Okay.
Yes. And okay, what we are going. Okay, this is maybe the best way to do this.
Yeah.
So yeah, in QIBO you can already import some pre-computed symbols like the Paulis you see here. But in general, you can do that manually if you want using the SymPy.
Eventually, Matteo, if you want, you can click on the link on the tutorial in the documentation. I think there was how to write custom Hamiltonians.
Yes, maybe it's much better.
No, it was on the left in the page where you were before. Yes, see how to define. Yes, I think this should answer something. Yes, maybe yes. Maybe below.
See.
Yes.
Here, maybe.
Yes. Yes.
Okay.
Yeah, so you import the symbols. Okay. Yeah, that was my question. So this is kind of the nearest neighbor Ising model.
Yeah.
And now I could
Okay.
also zip it with some lists and put some random values and then see whether that kicks. And maybe I get lucky and then we get the drop. I mean,
Yeah, I
yeah,
think I think this is the easiest way to play with the symbols in QIBO.
yeah. Okay.
I would suggest in case to use hyperopt and to maybe let hyperopt to do this for us.
Yeah, so I could run hyperopt on some added values here, some AI, and then find those values using hyperopt. Okay.
Yes. For example, yes.
Yeah.
And then the important thing is after you have the symbolic form of the Hamiltonian, you need to call this Hamiltonians.symbolic Hamiltonian, which wraps the symbol and makes it an Hamiltonian, a QIBO Hamiltonian with all the
QIBO
features.
Hamiltonian, and then I will have this translation from Pauli's into the Hamiltonians, because if I run on hyperopt, I need to be careful, no, so that it runs fast.
Yeah, hyperopt doesn't care about what happens inside the objective function in the end. So that step you can do how you prefer. But then if you want to use the Hamiltonian like an Hamiltonian in QIBO, you must to build it like an Hamiltonian. So you should provide to the symbolic Hamiltonian wrapper the symbol.
Yeah. Because I'm still wondering, sometimes if I will work with like 15 qubits, sometimes the creation of those Hamiltonians actually takes a bit of time. But for like small examples, this is maybe the best thing, and we can finish the tutorial here. And how to do it faster for like larger Hamiltonians, because the optimization would involve creating many Hamiltonians, no? So sometimes it can become a bit costly, and part of the optimization time might be the over and over creation. But
yes, if we proceed with the
story.
hyper optimization approach like this, it's costly by default. Yes, if we have some wiser method like a gradient descent or something like this, for sure will be easier at some point.
Okay, thank you very much. Would you like to summarize something, or so we saw top down how to use the class and everything?
Yeah, I think I don't know if you want to if you want me share again the tutorial, but yeah, what happened here is basically the following. We defined an Hamiltonian using QIBO. You can do it as you want using the symbols or whatever. Also, you can provide directly the matrix, and an Hamiltonian can be built on top of the matrix. And then what we did is to present the double bracket flow components that are the flow generator type that should be should be set in order to define how to evolve the Hamiltonian, and then the double bracket flow class that if you call, you perform one iteration. This is the super summary of the tutorial, I guess.
Yeah. So in this case, we have the solvable model, so the canonical flow is getting stuck, and then we tried how to change it. And the code is already available. It's just on a different branch, which is not the official branch, right? So we were showing that. And
correct.
Yeah. Okay. Well, thank you very much. This is it's a very elegant.
Is available not with the hyper optimizer, because we still need to merge it in the WIP pull request. But I mean, if you in some branch, yes.
If you switch to a branch, then it's directly reproducible, and at some point it will be merged.
Yeah, but I suppose that in less than 1 week we will merge to main. So I mean, you will found directly on QIBO main.
Or eventually we can also send some instructions if you want to start to playing with this, even if before we merge it. if you want.
Yeah, no, I'm just saying in general, if in a few months somebody sees it, then it should be already merged by then. But if somebody sees it today, then we can also contribute directly and find it on the branch.
Yes.
Because sometimes it's not, there's a lot of happening in QIBO, so just to keep track. Okay, great. Thanks so much for the tutorial. I finished the recording here. Thank you.